Hi everyone, welcome to Vedantu J English. I'm Diksha Kaushal, your chemistry master teacher. So everybody, how are you all? And very good evening to all of you. So guys, today I'm going to do thermochemistry. We'll do Gibbs Helmholtz equation. We'll understand about different questions, because you will see today theory part will be very less, but the questions part will be more here. Because to understand thermochemistry, you need to understand what kind of questions that they have already asked you in these past years. And especially I'll be picking up 2025 questions here. And next week we are going to complete chemical equilibrium, and rest of the chapters that we are left with, right, we are going to do it within these 15 or 20 days itself, right, so that we can complete the full syllabus. And revision is going on side by side, as you know that, right? So guys, let's start. And tomorrow at 6 a.m. as well, Shreyas sir has his session of CYQs, right? Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, 6 a.m. is going to be one session for all of you, right? Okay, so the early morning birds also can watch this session at 6 a.m. And that will be purely practice questions, really good questions we are going to pick up from chapters, right? And I'll be taking your class on Wednesday and Thursday, right? So because practice revision should go side by side as we are doing the theory part, right? Okay, everybody. So if you're ready for that, do let me know. Hi, hello, Jasveer, Louis, then Pavan, Chandu, Soda. How are you all? Tell me. Shall we start? Shall we start the session? Are you all ready? Have you hit the like button on there or not? Have you hit the like button, students? Yes, everybody. So, let's start the session. Very important session we are going to do, right? Because most of the students skip this part, and I'll show you that they ask you question from thermochemistry, right? And it's very easy. It's so easy kind of questions are there. There is no formula that you have to cram here. It's just a matter of understanding the definition, understanding things here, right? Okay, so let's see. Yes, let's see. Guys, because of some family emergency, right, it was postponed, but I am here today, right, taking your class. So let's see second law of thermodynamics first, right? So second law of thermodynamics has three statements here. First is Clausius statement, that is, it is impossible to move, impossible for heat to move by itself from a low temperature to high temperature. Now, first statement that is saying, as we know that temperature always, if I say, goes from hot body to cool body, that means spontaneously the temperature moves in direction of high temperature to low temperature, right? Never you will see the flow of heat from cold body to hot body spontaneously. So that is Clausius statement, that from the cold body, that means low temperature to high temperature, heat cannot move by itself. It should move by some external force. If you are applying that, that means that will be a non-spontaneous process. So that is given by Kelvin's statement. No process is possible in which sole result is the absorption of heat from reservoir and its complete conversion into work. Now Kelvin is saying that it's not possible that some heat is being absorbed by the body and all of that is heat is converted to the work. There is some wastage of heat as well, right? So that is Kelvin's statement for second law of thermodynamics, that some wastage will be there. All of heat is not converted into work, right? Then Boltzmann's statement is all spontaneous processes, spontaneous means that are occurring by itself, or naturally occurring processes are thermodynamically irreversible. That means we are saying that all the processes, right, they are thermodynamic, naturally occurring processes which are spontaneous, they are going to be They are going to be what? They are going to be irreversible processes, that is given by Boltzmann, right? Without the help of an external agency, a spontaneous process cannot be reversed. A process that is happening by itself, right, it cannot be reversed. That means all the naturally occurring spontaneous processes are irreversible. They will not go back in the direction without the use of any external agency, right? Now if you see this here, now basically this second law of thermodynamics talks a lot about spontaneity and all, right? So for that, first we have already discussed about entropy, so we'll discuss more in detail of that. The entropy of universe increases in a spontaneous process. If you talk about the entropy of this whole universe, right, that will, now this is a very beautiful and very important statement that we have seen in our daily life as well, right? We are growing old, right? We don't reverse back. Do we age like this? Firstly, we are born up. There is a movie that is based on this thing where a man, I think, born as an old person and then he reverses back. I think he or she reverses back, right? But otherwise, that's just a movie. But otherwise, what happens, right? We are born, right? Then our age is increasing, right? So that's the reason. That means entropy, randomness, disorderness of this universe is constantly increasing. Reactions are occurring, that means entropy is increasing here. More the reactions are occurring, more entropy will be there. Big Bang theory is based on that thing, that entropy of the universe is increasing. So this might seem a very simple statement, but so many theories are based on this thing. So it's actually a very important thing that the entropy of the universe increases in a spontaneous process. If you talk about a spontaneous process that is occurring by itself, the naturally occurring processes, in those cases entropy of universe is increasing and it remains unchanged in an equilibrium process. If you talk about an equilibrium process, it will remain unchanged. That means entropy will not change in the equilibrium system. So for a spontaneous process, delta S of universes, delta of your system plus delta S of surrounding is greater than zero. That's a very important thing to understand, that if I talk about a spontaneous process, entropy of this universe is increasing. This universe accounts for system and surrounding, both the things, the thing that we are focusing on and everything else apart from the cup or this bottle, whatever you are focusing on, right? So that means entropy is increasing. That will be positive here. Directly the question can be asked, which of the following is true for spontaneous process? They will give you this thing, they will give you this thing. For a spontaneous process, it is greater than zero. For a non-spontaneous process, it is less than zero, you can say, because for a spontaneous process, it is greater than zero, right? Then an equilibrium process, when we are saying it is at equilibrium, then we are saying it is not changing. That means the change, the delta, the change in this universe is, we are not saying entropy is zero. I am saying change in entropy is zero. Here, because entropy is always increasing, that means final is greater than initial. That is the reason this is positive. Here, final is equal to initial. Nowhere I am saying that entropy is zero at equilibrium. I am not saying entropy is zero at equilibrium. I am nowhere saying that. I am saying that at equilibrium process, the change in entropy is zero. The change is zero. And here the change is positive. Right? Okay. Understood? So, next is, when a system is in equilibrium, the entropy is maximum. We are saying at equilibrium, it is at its maximum randomness, maximum entropy. You go forward, you go backward, its entropy will decrease in that case, and the change in entropy is going to be zero at equilibrium. And this all we are discussing is at equilibrium, right? Then we can say that entropy of a spontaneous process, right? If I talk about a spontaneous process, entropy of a spontaneous process increases till it reaches maximum, and at equilibrium change in entropy is zero. So what is the case here? What is the case here? How you can simplify this? Entropy increases to maximum. These statements are very important. Increases to, usually students in thermodynamics, they ignore these things, right? That's why I have made a specific lecture for this. These things are very important for you, right? So entropy increases to maximum, then reaches equilibrium, and then it will not change. At equilibrium, no change. No change in entropy is there. Right? At equilibrium, there is no change. Before that, it will reach to its maximum. Then at equilibrium, it's a constant thing. Tell me, is that clear to everybody? Unable to do in 11th physical chemistry, so I just don't want to do those chapters at this peak time. So could I skip to affect my JEE preparation marks? 11th grade physical chemistry. Achha, ma'am, I was unable to do 11th grade physical chemistry. I just don't want to do those chapters at this peak time. Should I skip that? I will not advise you to skip any chapter, right? In fact, I am making a video on this particular thing only. The chapters that you can skip, that you can afford to skip, and even those chapters that you're thinking I'll skip and I'll give only just 1 hour to them, just read out these 3-4 topics from there, and the chapters that you need to do in detail, right? So Galaxy, your answer will be there. I'll post that video by tomorrow or by Tuesday. That will be there, right? And that will be a complete detail, right? What are the things that you need to do with, what are the things that you can skip, right? It will be the best thing, and you will not find that anywhere else on YouTube, right? Because that is my personalized things that I'm actually working on that from the past 1 week. I'm analyzing the question papers. That's why I'm waiting for that, time to be there, because I'm taking my own sweet time to analyze all the papers, to understand things, so that when I give you something, when I tell you something, that is a full guarantee on it. So don't worry. The things that you can skip, the things that you must do, and the things that you can skip or do as well, right? Totally your choice. All of these categories I'll mention in that video, right? It will be crystal clear in your head, right? Okay, ma'am, please post by tomorrow. Chalo, I'll do that. Okay, I'll do that. Then by tomorrow, I'll do that, right? Okay. Yes, yes. Now, let's see the next thing. Spontaneous. It is this. Non-spontaneous, less than 0. And tell me, at equilibrium, shall I just write it here? At equilibrium. At equilibrium. You will write this here. At equilibrium. Delta S. At equilibrium. Delta S total, that means universe, is delta S system plus delta S surrounding. Tell me, is going to be equals to 0. So when it is positive, when it is negative, when it is 0, all of this is there. And here we are talking about the change here, right? Okay, yes. As the surrounding is at infinite heat, this is about second law of thermodynamics, okay? As the surrounding is at infinite heat reservoir. Now, if I talk about this surrounding has an infinite heat. I am a system. Suppose you're focusing on Diksha ma'am, right? Then Diksha ma'am is the system for you, right? System is confined in some place. System has some specific amount of energy. Diksha ma'am has some specific amount of energy, some specific amount of, I can't take like 100 hours of marathon, some specific amount of energy I have, right? So in the similar way, but surrounding, it is full of energy out there. So similarly, surrounding, if you talk about, it is a reservoir of energy. It is a reservoir of heat, right? So what we are saying, it has infinite heat reservoir. Hence, no amount of heat given to the surrounding. If I'm like, oh, I'm giving some heat to the surrounding, can cause turbulence in it. Hence, all the heat exchanges with surrounding are considered to be reversible. What do you mean by that, ma'am? There is an ocean, okay? And you are like, huh, I have this bottle and I have this much water in this. I'll just put it in the ocean so that I don't want the ocean to get dry. Ocean will be like, are you like stupid? I have so much of water. I don't need your water. This one bottle, what you will do with that? Right? So similarly, you have this reservoir of heat, that is the surrounding. You exchange heat. It is not going to do anything with the surroundings. Right? So that is the reason that we say that that change has not occurred. In you, the change has occurred. For you, this bottle, this water in this bottle is so much, right? This is so much. But for ocean, it is nothing. Similar thing, for surrounding, that heat is nothing, but for you, it is something, right? And that is why we say it is not going to cause turbulence here. Hence, all the heat exchanges with the surroundings are considered to be reversible. If you give it to the ocean, you can take it back. Ocean is not like, hey bro, I need that. Ocean be like, I will not do anything with your this much amount of heat, right? So that is reversible. And that's why when we talk about delta S, right, of system, you talk about Q reversible, right? Okay, that is because it is happening in reversible. So let's talk about delta S of surrounding. That is nothing but dq of surrounding by T. That is by the definition. For surrounding, T is constant. Now, are you able to think why for surrounding? Uh, what is all going on? Sorry and thank you in the chat box. Huh? What is all going on, guys? So if you see, for surrounding, T is constant, right? Temperature is constant here. Temperature is not changing. For ocean, you give it little bit water, ocean will be like, my weight will not change, buddy. My weight will not change here. It is same only, right? So you can say for surrounding, T is constant. T is not changing. dq, if you say the heat that is there, is it changing? No, dq is also same, right? Heat you are exchanging to ocean, there is no effect, there is no temperature effect there. So you will not write dq, you will not write dt, you will just write Q of surrounding by temperature. No change is there in the surrounding. But the law of conservation of energy states uh, Q of surrounding is minus of system. According to law of conservation, if system is giving some energy to the surrounding, right? System is giving some energy to the surrounding, that Q of surrounding should be equals to minus of system is giving that energy. So you, because that is a conservation, the heat that is given, it will be converted in some amount. To ocean it is not effect, but we are giving some energy, right? So that will be system is giving this energy to it. So that's why Q surrounding is nothing but it is negative of Q system that was originally there with the system. So delta S of surrounding will become, in terms of system, it will become minus Q of system by T, right? And this formula you can remember, right? I'll just mark this in a box, right? Then if you talk about this thing, this is A, this is B. Now we are saying that if you're going from state A to state B, okay, let's say you are going through this process, this is a reversible process. Let's say you are going through this process, this is a irreversible process, right? For state A to state B, you can have two things here. Just give me a second. Wait a second. Yes. Okay. Just give me a second. Huh. Okay. Why it is minus? Why minus for Q system? Minus is there for Q system because it is releasing the energy, no? It is absorbing the energy, right? So that's why it is absorbing. No doubt for ocean it is no effect. You give it one glass of water to ocean, it is not effect. But you have given something, right? For you it matters, right? For you, you are like, I could have just drank that glass of water because for you it matters. For ocean it doesn't matter. Just like for you, if uh, if you have to gift Mr. Ambani a diamond set or a big bungalow, for you it would take you like years and years to build it and then gift it, right? For you it is like you're earning. For Mr. Ambani, it's like, okay, um, it's okay. Like it doesn't matter. Like I do gift it to random people. How does like 100 crores or 1 2 crores matter to him? 1 2 crore is like 10 rupees for him, right? For you, it is like 1 crore is like your full, like, ma'am. And for me, it is like, oh my god, I'll have to work for 16, 17, 20, 30 years to have that 1 crore rupees. To Mr. Ambani, it's like half a day or maybe 1 hour he is earning 100 crores, right? So for system it is matters, for surrounding it doesn't matter, right? But still we'll equate them. Why? Because for system it matters, and system is absorbing the energy, so it's positive. Surrounding is releasing the energy, giving the energy, so it's negative. Okay, understood? That's why we have put here minus q system by t. Now we are saying that, what if I say for state A to state B, you are going through delta S of reversible or delta S of irreversible, two ways you are going through to state B. As S is the state function, delta S will not depend on the path. Such an important thing. Entropy was a state function, and state function means it will not be dependent upon path. So whether it goes through reversible or it goes through irreversible, how does it even matter? So we can say that delta S of reversible is equals to delta S of irreversible. It doesn't matter whatever path it follows, its entropy is going to remain the same. So you can say delta S of irreversible or reversible will be dq reversible by t for the reversible path or even the irreversible path, because that is going to be the same. As this is there for the reversible path, the same thing will be there for the irreversible path. Okay? Yes, everybody? Now, moving ahead, right? Now, let's understand a very important equation. So many questions are asked based on Gibbs Helmholtz equation. Mark it important, very, very, very important, very, 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 very important, right? Now, these are the kind of questions, those who are thinking that I'll skip thermodynamics, skip it. Don't skip this thing, because it will not take you that much time to understand this question, right? So it's very simple and very easy, and the questions are asked from this particular part of thermodynamics. That's why I will never recommend for any student to skip entirely thermodynamics. There are some places in thermodynamics, just like today's lecture that we are doing today. There are so many simple questions you will see there in the PYQs. Right now the PYQs are going to start because theory will be less, right? Gibbs Helmholtz equation. If I say mathematically, the process of carbon in the form of diamond turning into graphite is a spontaneous process, right? Carbon in the form of diamond turning into graphite, this could be determined by Gibbs free enthalpy. How some processes are spontaneous, let's understand. That is determined by this Gibbs Helmholtz equation. G is equals to H minus Ts. Now temperature I am saying is constant, so it will become delta G is equals to delta H minus T delta S. That will be the equation here, where this is Gibbs energy, this is Gibbs energy, that is a useful work done. Gibbs energy is a useful, how much work is done in a useful way, right? Delta H is the enthalpy. You can write this over here. Delta H is enthalpy. That we know it can be positive, it can be negative. T is the temperature, delta S is the entropy, right? Delta S is the entropy. Now let's see, ma'am, but what is the conclusion of Gibbs free enthalpy? See, Gibbs free enthalpy is actually going to tell you whether it's spontaneous or non-spontaneous, and it will never go wrong, right? There is no exception to it, right? So delta G, if it is coming out to be negative, it's a spontaneous process. If it is positive, it's a non-spontaneous process. If it is equals to 0, it's at equilibrium. As simple as that. Okay. Now if I see According to delta H is positive, this is negative, you may have spontaneous, non-spontaneous processes. So let's understand that. Okay, let's understand that. So if you say, ma'am, let's take a case where delta H is negative and delta S is positive. If this is negative and this is positive, for the overall equation to be negative, what you should have? If T delta S becomes, if this is positive, this is negative, right? This is positive, this is negative, this is positive. This will become minus of delta H minus of T delta S. So always it is going to be negative no matter what. Whether this is greater or this is greater, it is always going to be a spontaneous process, right? Next is, if this is positive, enthalpy is positive, heat is absorbed by the system, and this is negative, right? Minus minus will become plus, so this is delta H plus T delta S. So overall, if you say no matter delta H is greater or T delta S is greater, this is always going to be a non-spontaneous process having positive delta G. Okay, next is, if I say delta H is negative, T delta S is negative. This is negative and this is also negative. This negative negative will become positive, so it will become minus of delta S and minus minus plus of T delta S. And when I put these points, that means I am talking about only the values, not the signs here, right? Now, to make this spontaneous, delta H has to be greater. Otherwise, because 7 minus 5 will be positive, but 5 minus 7 will be negative. So that means this has to be greater. So that means delta H has to be greater than T delta S to make the whole process as spontaneous. Otherwise, this is going to be a non-spontaneous process, right? Okay. Next is, ma'am, delta H is positive and this is also positive. If I say this is positive, this is positive, this will again become delta H minus T delta S. Now which has to be greater to make it negative? This has to be greater. So T delta S has to be greater than delta H to make it negative and a spontaneous process. Okay, tell me. Yes? Delta tells Louis, it's a sequence, na? When you study atomic structure, you firstly go through Thomson model, then Rutherford model, right? Okay, so that's a sequence. Now overall Gibbs free enthalpy has to be negative. Now in that case, this can be positive, negative, negative, positive. These things can be there, right? But what will define delta G? That is delta G. The spontaneity will be defined by delta G. Okay. Firstly, we were defining it by entropy. Then we understood that there will be some points where we won't be able to tell that, right? That's how scientists made this equation, that this is the equation that you will use to tell the spontaneity, which will be based on enthalpy and entropy as well, right? Okay. Yes, everybody. Gemina, Darkin, why are you deleting your messages? Ujjwal, what has happened? What you guys are talking that you don't want me to see? Huh? What is that secret talks that you are doing? That you are like literally hiding from me. From me. Ma'am, we will not let you see that. Huh? Let's see. JEE Mains 2019 question, that is the reaction. This reaction is given to you for delta HR is this, delta H reaction is this, and delta S of reaction is this, right? Is it variable? Which one? Delta G, definitely it's variable. It can, according to the reaction conditions, it will change, right? Okay, is it variable meaning what? In what sense you're asking me that? Ma'am, delta S and delta H we are talking because we want to know that as well, right? Based on Now delta S, if let's say it is not given, I know that delta S is nothing but Q by T. Then Q by T will be given to you, right? And delta H also you have, no, you know that delta H you can calculate like this, that we have discussed in the last class. You can calculate like this. Let's say delta H is not given to you. You can calculate from these two equations, right? So it's just a way how you solve this, right? The reaction is given, delta H is given, delta R is delta S is given. They are saying is not feasible. The temperature above which the reaction will be feasible will be what? Now we are saying at 25 degrees Celsius, it is not feasible. That means it's a non-spontaneous process here. To make this a spontaneous process, we know that delta G has to be negative, right? That means delta H, I'll just write it as delta G, not delta GR. Okay, it will then, take a lot of time to write R again and again. Delta H minus T delta S has to be negative. You take it here, that means delta H should be less than T delta S, right? Now that means temperature has to be greater than delta H by delta S. Now you put the values here and you will get your answer. Delta H is what, everybody? Delta H is what, ma'am? This is delta H. That means it has to be greater than 491.1. This is kilojoule and that is joule. So kilojoule to joule means multiplied by 10 raised to power 3 divided by 198, right? And you solve this is nothing but joule per mole, and this is nothing but this is joule per Kelvin. This is also one thing. Achha, this is also per mole. Okay, my bad. I thought here per mole is not written. If here per mole is not written, then I'll have to convert it into per mole. Per mole means I'll divide it by number of moles then, right? So it is already given that much complication, so they will not do. 198, this is joule per mole per Kelvin, and these all will cancel. You will have Kelvin here. So temperature will be greater than, solve this value and you will get your answer, right? Solve this value, I think it should be 2040. I think B should be the correct answer. I'm not sure. I have not calculated, but I think, okay, it is coming out to be not B, but it is coming out to be 2480.3. This is the correct answer here. So you can solve this doing the calculation and you will get your answer. That is, A is the correct answer here. Okay, everyone, right? Yes, calculation hai, that is there. Now JEE 2023 question that we have here based on the same thing, right? Based on the same thing. JEE 2023 question that we have, that is for independent process at 300 Kelvin. If you have an independent process at 300 Kelvin, right, let's say A, B, C, D, this is delta H is given, okay. Now they are saying the number of non-spontaneous processes that you have to figure out here. Delta G is equals to delta H minus T delta S. For a non-spontaneous process, if this is negative, this is positive, it will be non-spontaneous. That means this, no. They're asking you non-spontaneous process. This will always be spontaneous. Always it's a spontaneous. I'm not even solving this. If this is positive and this is negative, positive, this is always a non-spontaneous process. Always a non-spontaneous. If this is negative, it will become delta H mod plus T delta S mod. So it will always going to be positive and non-spontaneous process, right? What about this one? Both are negative. This is also negative, this is also negative. So it will become delta H, that is minus of 25. Temperature is 300. This will become minus of minus 80 plus of 300, right? You'll put it here, you will solve it. This is minus 25. Definitely it is greater. So it is 25 plus 80 into 300. Can I say, guys, this is definitely greater, right? So it is overall positive. So this is obviously going to be a non-spontaneous process. Now let's see this one. This is 22, this is 20, right? So let's put it here. This is 22, this is minus, T is 300, this is 20. So this is definitely, this temperature is greater, right? This value is greater, so it is definitely going to be overall negative. That means this is going to be a spontaneous process. So 2 are non-spontaneous, 2 are spontaneous. So you can say number of non-spontaneous processes are 2. Okay, everybody, tell me, everyone, in the chat box if that is clear to all of you or not. Right, everybody? See, it was not at all a difficult question, and just 2 years back they have asked you, and even last year they have asked quite simple question based on this, right? Okay. Now let's do third law of thermodynamics. Quite simple, quite easy, right? We'll see and we'll find out what exactly is this, why it is like this, okay, all these things. So if I talk about, yes, Ujjwal, yes, Louis, Sairam, very good. What about others? Hi, Harika. Yes, everybody, awake, Galaxy. Everyone awake here? Not sleeping? Yes, Surya. Everyone awake, right? No one is sleeping here in the class? Yes, Sai. Okay, let's do this. Third law of thermodynamics, right? Okay. Yes. Now, if you see this here, right? Actually, I'll just draw the atoms here. If I can copy them. Okay. I think that is not visible to you, so I'm just drawing a lattice here. This is a lattice. This is a perfectly crystalline lattice. Can you see? That is, ma'am, no, ma'am, this is not perfect. Wait a minute. Let me make it perfect, guys. This is a perfectly crystalline lattice. Perfectly crystalline means all the atoms are beautifully aligned. That is a perfectly crystalline lattice. So here we are not, and this na question they can ask you, aise to they don't ask you as such question from here, right? But I'll tell you what they can ask you is statement based questions on that, right? Let me see, actually there is no option to copy here. Even if there is, I don't know. From the past 2 years, I'm trying to find out. Actually, 3 years, I'm trying to find out how to copy this. If you ever get to know, then please do let me know. Help your teacher out, because teacher is little non-technical, right? Oof, it's quite irritating, guys. I don't know how people do handwork, na. I to just hate it. Doing all these things. Oof, that's so irritating to see. It's not actually perfectly aligned by me, right? Okay, I'll just put it here and I'll just put this here. Okay. Okay. Now the crystal, which is not so perfect by your Diksha ma'am, but you can take this perfect, but you can call it little bit perfect. Okay. Okay, not so perfect, but you can call it perfect. Will you? Will you manage that much? Okay. So this is your given compound is polar protic. Arey Venka, why we are talking about SN1, SN2? We'll talk. We have already talked about that, right? You can go and check out that, right? Okay, it's quite irritating. Yes, the Gola part is quite irritating. My hands were like, ah. Okay, so yes. Now, the entropy of perfectly crystalline solid may be taken as 0. Now, we are saying that you take the entropy of perfectly crystalline solids that you have seen. It's quite tough to make perfectly crystalline solids where atoms are properly in symmetry, properly aligned. That is a perfectly crystalline solid. And third law of thermodynamics states that it can be taken as 0. The entropy here, we take the entropy of a perfectly crystalline solid as 0 at the absolute temperature. At which thing? At the absolute at the absolute 0 of temperature. That means absolute 0 is 0 Kelvin. That is not in degrees Celsius, that is in Kelvin. Right? When the temperature, that means we can say this over here, when the temperature is 0 Kelvin, then the entropy is going to be 0. Okay, when the temperature is 0 Kelvin, then the entropy is going to be 0. But ma'am, how can you say that? Ma'am, we want to know that. Ma'am, how can you just say, tell us a statement and we'll believe? How? Let's see. Right? Because scientists, that is in your syllabus, I'll teach you that. Right? The entropy of a perfectly crystalline solid may be taken as 0 at the absolute 0 of the temperature. Let's see how. It helps in calculation of absolute entropy of a system at any temperature T. Right? You can calculate the absolute entropy. Let's see. See, let's say S0 is the entropy at 0 Kelvin and this is the entropy at T Kelvin. Okay? Two temperatures you have. This is at 0 Kelvin, this is T Kelvin. Now, delta S is nothing but it is S, that is entropy at T Kelvin, right? That is S minus entropy at 0 Kelvin, that is S naught. So, S minus S naught, this we have already seen that this is 0, right? This we already know that this is 0. 0 at 0 Kelvin by third law of thermodynamics. Third law of thermodynamics is telling you that this you have to take 0. This is a law that is proposed by thermodynamics that it will be 0. If this is 0, right, I'll just put it 0. And what is this S here, right? What is this S here, right? Let's see that. This S here in terms of this T is what? That is going to be Cp dt. Okay, that is the value of entropy, that is Cp dt by T. Okay, that we have put the value of entropy here, that is Cp, heat capacity at a constant pressure into dt by T, right? And then you solve it from 0 to T Kelvin, that will become Cp, because see here what you will do, Cp you will take common here, this will become 0 to T and this is dt by, this is 1 by T, and this will become Cp and this is ln of T, right? And this is Cp ln of T. Ln of T is nothing but it is log 2.303 log of T, and that is the equation that you must remember. Okay, right? Where Cp is assumed to be constant at a range of 0 to T. Okay, tell me, is that clear? Is that clear, everybody? Okay, Cp is assumed to be constant. That's how we have taken it out, right? This is another formula that you have, that Cp S is equals to Cp ln of T. Just remember this much. Cp is equals to, sorry, delta S is equals to Cp ln of T. Okay. Now, let's see this thing here. Third law of thermodynamics, right? What you have next? Third law of thermodynamics. Advait is saying, ma'am, which is the most weightage topic. See, first law of thermodynamics is most important, and when I say first law of thermodynamics, I include this work relations, all these things in that. Especially if you are selective, then you must do work for isothermal reversible, isothermal irreversible, and adiabatic. These are like three very important formulas. Then first law of thermodynamics, standard formula, delta U is equals to W plus Q. Then this Gibbs Helmholtz equation that I taught you, the questions on this. delta U and delta H relation, right? These are like 3-4 formulas that are very important. Firstly, work related formulas of isothermal adiabatic, then first law of thermodynamics relation, then Gibbs Helmholtz and delta H delta. These are the formulas from where definitely like 1 or 2 questions you will see. Then one question from thermochemistry that we are going to start now, because it's a simple, you just have to go through the terms and definitely you will not do mistake in thermochemistry. Thermochemistry you don't even have to revise. Once you understand this, it will be in your head. We are going to start it after this. We are going to start thermochemistry. If you see this now, this now I'll only teach you what is important for a chemical reaction. Let's say this delta S of system is what is ever is product and minus, this should be minus over here, right? Minus of reactant. Delta is standard molar entropy. It can be calculating using third law of thermodynamics. That is nothing but delta S of surrounding is Q system by T, that we have already done, right? Q system, that is nothing but heat. You can also write it by delta H system of T. Now, if you see for a perfectly crystalline substance at 0 Kelvin, entropy is going to be 0, right? Okay. Now if you see for phase transformations, now you see this thing here, that delta S, we are saying what is delta. First thing here, so we have said that delta S is nothing. If you want to calculate the change, that will always be product minus reactant. Remember this, okay? Product minus reactant. It's not reactant minus product, it's product minus reactants. Then remember that delta S of surrounding is minus of delta H by T. That means if I talk about the phase transforms, then if I talk about fusion, that means melting, then delta S fusion will be equals to delta H of fusion by T, right? If I talk about delta S of fusion in terms of delta U, that will be equals to delta U fusion by T. If I talk about it in vaporization, that will be delta S vaporization, delta H vaporization by T at constant pressure. And if volume is constant, delta H will be replaced by delta U. But a simple thing is that delta S is nothing but Q by T. Okay. If this Q is at constant volume, this will become QV, that is nothing but delta H by T. If this is at constant pressure, this will become QP, that is nothing but delta, this will be delta U by T and this will be delta H by T. That is the simple thing that we should know. You don't have to cram these formulas. Just remember, we are going to apply this thing here as well. In delta S, it can be in terms of delta U, it can be in terms of delta H. If you have fusion, you will write fusion. If you have vaporization, you will write vaporization. Similarly here. Okay. Yes, everybody, to write it in a beautiful way, I'll just write this here. If Q, we say Q by T, delta S is equals to Q by T. If I talk about two cases here, if I say at constant volume, this is nothing but delta U by T. At constant pressure, it is nothing but delta H by T. Okay, that's all what you have to remember here, right? Okay, this is what just in a fashionable way they have written it here. Otherwise, just remember this thing, right? Okay, because there is because there is no perfectly crystalline solid. Perfectly crystalline solid is a very hypothetical thing, right? That is the reason. Very good question, Louis. Very good question. If ma'am entropy entropy at absolute zero is zero for a perfectly crystalline solid, then why many substances have non-zero entropy? Because they are not perfectly crystalline, and it is very hypothetical to have a perfectly crystalline solid. It's just like no human is perfect, na solids are also not perfect, right? Okay. Yes. So now let's understand thermochemistry. It's quite a simple and an important thing to understand, right? And it weighs a lot. Usually students think that, ma'am, this has no importance, but I'll tell you how it is important. I'll tell you why it is important. Okay? Yes, everybody, let's talk about that. Let's talk about that. Manor Dubey is like, ma'am, everything is important. Yes, but you know, some students do what kind of mistakes? They will spend a lot of time doing these things, yet they are not on that of important side, right? What is on the important side is this thing, this thing, this thing. And that's why to understand what you have to just go through just once and what you have to be pro in, that you must know, right? That is very important thing for you to know when you start a chapter. I'll not be directly talking about this thing here. Let's talk about thermochemistry one by one. Okay, now a lot of theory part, but question, theory part plus question will be there, but questions you can only solve if you know the theory. And if you have just done the theory, you have not solved the question, trust me, theory will not help. In this case, theory will not help, and doing just the question will also not help, because if you don't know what is that heat, you won't be able to understand the question. But if you understand both in a symmetry, trust me, this is the last time you are doing thermochemistry. After this, no revision is needed. Only no revision is needed here. Just once go through this one or twice and just solve the questions, that's it, right? So thermochemistry, all chemical processes are associated with energy changes. Energy changes are there in a chemical reaction. The thermochemical equation represents both material and the energy change. A balanced chemical equation. Now what we are saying, we can see that physical means how molecules are changing, how they are balanced, how energy is being extracted, how energy is being released. That means we are showing both material and energy change here. So balanced equation not only indicates quantity of reactant product, but also indicates the amount of heat evolved or absorbed. Now if you see, when heat is on this side, that means delta H is released, that is minus of 285.8 kilojoule per mole. And you know what is all this? This is your thermochemical equation. A thermochemical equation where we tell the heat change as well, right? That is a thermochemical balanced equation, right? So let's talk about any reaction will lead to the change in the energy. For reactant to product you are going, energy change will be there, right? That we call as enthalpy. That is called as reaction enthalpy, or we say enthalpy of the reaction, which is represented by delta HR. Now whatever I'll write here in the subscript, that are very important. Firstly, any reaction you have in a balanced chemical equation, whatever is the reactant, whatever is the product, what is the energy associated with that particular reaction is called energy of that reaction, right? Amount of heat lost, heat can be lost or heat can be gained. If heat is lost, then it is called as released, that is negative, and if heat is gained, it is positive. In a chemical reaction, when all the reactant and products are maintained at the same temperature, now condition is that all the reactants and the products are at same temperature and pressure. So in thermochemistry, you will not talk about formulas here. You will not talk about volume, pressure, temperature. You will not talk about that. We will just talk about energy. We will just talk about heat energy, energy of the reaction, heat enthalpy of the reaction. So that is called as enthalpy change of the chemical reaction, that is delta HR. That is always sum of enthalpies of products minus sum of enthalpies of reactants. If enthalpies are given, right? So it will be product minus reactant, when V is the stoichiometric coefficient of reactant, this is product. Okay, always remember this is product and this is reactant. If the reaction is reversed, then the sign of delta H is also reversed. If a forward reaction is positive, backward reaction will be negative. Okay, so if I say if the reaction is reversed, delta H is also reversed for that reaction. Okay. When heat is evolved during the reaction, that is evolved means it is released, that is negative. If it is absorbed, that is positive. That is about delta H of that reaction. Now let's see this question here. Very important, that quantities of reactants involved, if you see in this particular reaction, it is minus 285.5. If I multiply this, I have just multiplied it by 2. If any reaction is multiplied or divided by any stoichiometric coefficient, its heat of enthalpy, heat of enthalpy, I'm saying enthalpy of that reaction is going to change. If I'm multiplying this by 2, I'm also going to multiply this by 2, right? Okay, heat of the reaction is doubled. If I say this is a reaction, H2 plus half of O2 give rise to H2O liquid, then this is the heat that is evolved. If it is gas, then there is a different heat. So every reaction, they will have their own specific heat, right? But yes, if you multiply it divided by some coefficient, if you reverse the reaction, then in the reverse the sign will change. If you multiply it or divide, the same thing will happen to the delta H of that particular reaction. Okay, now if you see allotropic modification, this is from carbon graphite, you are forming carbon dioxide. This is from carbon this is from carbon diamond, this is from carbon graphite. Now heat of this particular heat of this particular reaction is also different. So even if you're using the same element but in a different allotropic form, here what we saw, that if you're making a different phase here, this is liquid, this is gas, even then delta H is different. This is gas and this is liquid. Even now delta H is different. If you see here, this is carbon diamond and this is carbon graphite. Now there is also another change here. That also means heat of the reaction will be different for different allotropic form. It's not like allotropic forms will have same heat of reactions. They are going to have different heat of reaction, right? Now if you see condition of constant pressure or volume is there, heat changes at constant volume are expressed as, now I will write it as delta U, because you have done it in delta U itself, right? Some, I told you in some books it is also written as delta E, right? Can you tell me what is this, ma'am? This is delta, this is, ma'am, QV is equals to delta U and QP is equals to delta H. This is, so I have told you so many times, this is a very important formula, right? Very important thing. Now heat changes at constant volume and pressure, that we have seen how they are expressed. And if I talk about temperature, heat of reaction or enthalpy of reaction also depends upon the temperature. That's why we are saying it has to be constant, right? On the temperature at which the reaction is carried out. This is due to the variation in the heat capacity of the system with the temperature. So we know that heat capacity is equals to Q by T. So as you change the volume, if volume is constant or pressure is constant, right, that will be dependent on volume and pressure, right? If temperature also changes, heat capacity changes. So heat capacity depends upon volume, pressure, temperature, all of these things. This is due to the variation of heat capacity. Due to this reason, enthalpy of reactions are calculated and expressed at a standard temperature. Now that's why we are keeping them constant. Why we are keeping volume constant? Because we want to have heat changes at constant pressure and temperature, because if you variate the temperature or pressure, eventually the heat changes are going to vary. Temperature as well, if you vary the temperature, heat enthalpy of that reaction is going to change. That's why some reactions are done at a specific temperature in a specific environmental conditions, and that is the reason we take standard temperature here, that is 25 degrees, and you will not see that temperature is variated in these questions. Okay, Now let's talk about standard enthalpy. Ma'am, what is standard enthalpy? What are standard conditions? See, standard enthalpy is enthalpy change accompanying when all the reactants are taken at standard state, right? Standard state means the standard conditions are solid, liquid, gas should be at 1 bar, pressure should be 1 bar. For substances in a solution, concentration should be 1 molar, right? Standard condition does not specify any temperature. This temperature is usually taken as 298 Kelvin. In usual cases, we take it as 298, but it is not considered as a standard temperature, but we take it as 298 Kelvin for these reactions. And standard states, if you see, right? Standard states like you have carbon is standard in form of solid or graphite, sulfur solid rhombic sulfur is standard, phosphorus white sulfur is standard. So this you must know what are the standard forms here, right? Okay, let's see. Now we'll talk about one type of enthalpy here. Which thing do you want me to repeat, Sai? Tell me. Why does real time depend on 290? What is temperature? You can take any temperature, Louis. You can take any temperature. Okay, it's not like it's just by convention we take it as 298. But you can take any temperature. Temperature standard is not defined. But pressure is defined, concentration is defined. That pressure will be 1 bar, concentration will be 1 molar. That is defined. Okay? Yes? Uh, Ma'am, if enthalpy is a state function, then why don't we take ma'am, enthalpy, standard enthalpy, why can we get absolute enthalpy of a substance? Is a state function at 0 Kelvin you are defining the enthalpy. Standard does not define, standard and absolute has no relation with each other only. Standard we are defining because we want to study those reactions at a specific temperature so that different results do not occur, right? That's why we take standard conditions. These standard conditions are taken so that different results are not there, right? It's not because that you should only do this reaction at this temperature, at this pressure. It's because that we want to know at standard that everyone is doing this reaction at standard condition. What is the result that we are finding here? Okay, right? You will get the notes in the description box. There will be ask Ved. There you will click. You can get the doubts as well. You can ask your doubts related to this session as well, and you can also take your PDF from that link. Okay. Yes. Now here it is, enthalpy of neutralization. Now one by one I'm going to talk about. All of these are standard. Okay, standard means all of the enthalpies bitter that I'm going to discuss now will be at standard conditions, right? Okay, yes. What you are asking, the first lecture? No, this is not the first lecture. This is the third lecture. Okay, this is the third lecture. Okay, Kanga, you can watch the recorded version of that. What is the temperature is? Yes, definitely the value will be different for different temperature. That's why we are taking that. Usually we take this as the temperature where we are trying to study the enthalpy of reaction, right, on this temperature, because if we don't fix the temperature, enthalpies will vary here. Okay, right? Yes. Now, shall I start with different enthalpies, guys? First is very important, enthalpy of neutralization, where students have a lot of problem and the questions are asked here from the enthalpy of neutralization. Let's see that. Enthalpy of neutralization is the amount of heat that is released. We are saying the amount of heat released when 1 gram equivalent of an acid is neutralized by 1 gram equivalent of a base. Okay, that means 1 gram equivalent means only one H positive. Okay. So when 1 gram equivalent is nucleated by 1 gram equivalent of base, then the heat released is called as heat energy of neutralization. And if I say you have a strong acid, you have a strong base, then at that condition, the heat released will be this much. And this is only for strong acid. This is, I am telling you, for strong acid. Let's write it here. This is for strong acid and strong base. This is for strong acid and strong base. Okay, right? This is for strong acid and strong base. This is confusing, but see, you're going to eventually, when you see the questions, you're going to find it easy. Are why are you taking so much importance to the temperature? Yes, we fix the temperature because we want, now all these things that I'm discussing is at 298 Kelvin. We have fixed it because it will change if I change the temperature, right? According to temperature, things vary a lot. So you take fixed volume, fixed pressure, fixed temperature. Only then you say that we are discussing this at standard conditions, right? Pressure, volume, everything is fixed here. Volume means concentration is fixed. Concentration is 1 molar. Pressure has to be 1 bar. Temperature should be fixed and we are fixing it as 298 Kelvin. So everywhere I'll not mention it again and again, it is 298 Kelvin. We are studying it on 298 Kelvin, okay? So here for strong acid and strong base, the heat of neutralization is for 1 gram equivalent of an acid and 1 gram equivalent of base is minus 57.1 kilojoule per mole. That is minus 13.7 kilojoule per mole. Right? Okay, everybody, tell me. Now, for a strong acid and strong base, the heat of neutralization is always equal to this thing that we have discussed. For any other combination of acid and base, the heat is less than this. This is very important. For any other combination, heat is always less than what we have at standard condition for strong acid and strong base. Right? Heat will be always less than that. So let's see a question based on that. That is your 2024 question, where we are going to see what exactly happens here. Okay. So the question is, given below are two statements. One is labeled as assertion, other is labeled as reason. Okay, so assertion is enthalpy of neutralization for strong monobasic means only one OH negative, that means 1 gram equivalent, with monoacidic base is always this. Okay, that is true. Enthalpy of neutralization is the amount. What is enthalpy of neutralization? Is the amount of heat liberated when 1 mole of H positive ions furnished by acid combines with 1 mole of OH negative. That is also true, right? 1 gram equivalent or 1 mole, that is the same thing, right? To form 1 mole of water, right? And here that is called as enthalpy of neutralization. So both are true here. But if I say, right, both are true, and let's see if they are explaining each other or not. Let's see. Why enthalpy of neutralization of strong monobasic acid and this is always this? Because enthalpy of neutralization is the amount of heat liberated with 1 mole of this and this with 1 mole of this to form 1 mole of this. That means it will be fixed. Why it is always this? Because we are saying enthalpy of neutralization is fixed. We are telling that enthalpy of neutralization is of 1 mole only. Right, 1 mole of H positive and 1 mole of OH negative, that is not going to change, and that is why it is fixed. So we can say it is also explaining it. So answer will be that both A and R are true, but R is the correct explanation of A. Okay, and R is the correct explanation of A. Tell me yes. Yes, tell me. Pesera, do you really think I have two, three eyes? One eye when it is on the board, then I pause and then I look at your doubts, right? So I am not Lord Shiva that I have so many eyes that I can also look in the screen as well as when I'm studying, right? So, uh, because for a strong acid and strong base, it is fixed. Why it is fixed? Because always 1 mole of H positive will be strong. See, if I have 1 mole of HCl and 1 mole of NaOH, I know that all of 1 mole of H positive will be dissociated. All of this will be dissociated. So when you have strong acid and strong base, because of 100% dissociation, you will always have 1 mole of H positive and 1 mole of OH negative. But if I talk about a weak acid and a strong base, or a weak strong acid and a weak base, or both are weak, then 100% dissociation is not there. Not fully H positive and OH negative you will have, right? That is the reason to make it dissociate, right? More energy will be required. That means the heat energy released will be less, because energy will be given to the system as well to dissociate more ions, because it's not a strong acid or a strong base. That is why it will be less than the defined value for strong acid and strong base. Okay, what is actually happening is neutralization. Yes, neutralization is taking place in these cases. This is neutralization. I need 1 mole of this and 1 mole of this. If I have a strong acid and a strong base, they can easily, 1 mole will give me 1 mole H positive, 1 mole will give me 1 mole of OH negative, right? Easily. But if I have a weak acid like this, it is not going to dissociate 100%. So I'll have to use my energy also, right, in dissociating this thing. So it's the same situation. For example, you are preparing for JEE Mains. For example, you are preparing for JEE Mains, and if I say there will be some chapters where you don't need to revise, you just start the questions, so less energy is required there, you just practice. There are some chapters where you need to study the theory, then understand, then you see the questions, more energy is required here, right? So when you talk about weak acid or weak base, more energy is taken by the system, so less energy is given out, so less energy is released. Okay, tell me. Tell me, is that clear? Is that clear? Right, now let's talk about enthalpy of ionization or dissociation. Right, what is enthalpy of ionization or dissociation? Let's talk about that. Okay, everyone. So, first thing is enthalpy of neutralization for weak acid or base plus strong base or acid is equal to enthalpy of neutralization. This is very important. Enthalpy of ionization for weak acid or base plus enthalpy of neutralization of strong acid plus base. This is a point which will make you understand things more easily. One of the questions that why this is a beta, because whenever you have 1 mole of H positive and one, they are saying that if you have 1 mole of H positive and if you have 1 mole of OH negative, this much energy will be released, that they have seen experimentally that whenever you have 1 mole of H positive, 1 mole of OH negative, this value is released. Okay, this value is released whenever you have 1 mole of H positive or OH negative. Now, if I take a strong acid or a strong base, strong acid will be 100% dissociated, it is going to give me 1 mole. Strong base will be 100% dissociated, it is going to give me 1 mole. I don't need to dissociate that thing further. But if I have a weak acid, right, and a strong one, that means one of them is strong. Either the acid is strong or the base is strong. If I have anything which is weak, that weakness that you have, that means like you have CH3COH, like you have NH4OH. These are weak acid, this is weak base, they will not be 100% associated. But you want 1 mole of H positive. How do you make this 100% dissociated? By using enthalpy of ionization. You will have to dissociate it. You will have to ionize it, right? When you ionize it, you will require energy. So that is the reason, because this is fixed. This is minus 57. Here some X amount of energy you will use. Let's say 13 amount of energy you have used. So it will make it, let's say 10 amount of energy you have used. It will make it minus 47. So overall energy has decreased. That's why we say that enthalpy of neutralization of strong acid and strong base is greater than this. Why? Because when you have a weak thing, you require energy for ionization as well, right? Okay, tell me everybody, is that clear? Is that clear? Is that clear, everyone? So calculation of enthalpy of ionization of weak acid and weak base. The neutralization of weak acid, say HCN, with strong base can be represented in two forms. Let's say ionization, firstly I'll ionize this and some amount of energy is released, that I call delta H of ionization. Then in neutralization of this H positive, right? Then this OH negative, which is from, let's say, from a strong base. This is a weak acid, this is from a strong base. For weak acid, I need to put more efforts to ionize it. For strong base, I don't need to put any effort. For strong base, easily I have this. Now, when they combine, when they neutralize, they have minus 57.1 kilojoule per mole of energy. Overall reaction, this for complete neutralization of one equivalent of HCN, and with one equivalent of this, enthalpy change will be written as delta H of neutralization for a weak acid. That will be equals to this plus this. So that is, you can just write it as delta H of this. You can write, wait a minute, you can also write it as delta H of neutralization. I'll just write delta H neutralization of weak is equals to delta H of ionization minus 57.1. Okay, if you want to solve this, this will be neutralization of weak plus 57.1. okay, right? Because if you put this here strong, it will become nothing but delta H of weak plus 57.1. That will be delta H of ionization. Tell me, is that clear, everyone? Is that clear? Louis, you just asked the question. When I explain it specially for you, then you don't tell me if that was clear or not. If ma'am can answer your questions, you also can respond well, na? Tell me, is that clear to everybody what we discussed? How delta H neutralization of strong acid is related to delta H ionization and delta H of weak acid. Okay, now here's a question of JEE 2012 that they have asked based on this very same concept, right? The concept is the enthalpy of neutralization of NH4OH with HCl is this much. Neutralization of NH4OH, that means a weak base with strong acid is this much, right? And the enthalpy of neutralization of strong acid, here they have written 55.9, right? So maybe they have taken some other temperature here, that's why enthalpy is changing here. Okay, at 298 it is 57. If it is not given, you will take it as 57, right? But here they have written specially this value, so I'll take this value because maybe they have changed the temperature here, right? The enthalpy of ionization. So delta H of weak is equals to delta H of strong, neutralization of strong, plus delta H ionization, right? So delta H ionization will be equals to delta H weak minus delta H strong. Delta H of weak, when one of them is weak, neutralization is minus 51, which is definitely less than what you have for strong acid and strong base. 4, 6 minus of minus 50, it's they have written 55.90, 50.5.90. Solve it and you will get your answer, right? Okay, yes. Tell me, is that clear? Right, solve this and you will get your answer here, and that is going to be D is the correct answer for that one. Okay, now let's see more of it. What is delta H of atomization, right? Okay, those two were related to each other, that's why I told you that. Beta, you can tell me if that was clear or not. That much you can answer. Does it hurt your hand so much, right, to write it yes ma'am, or is it that of a big task, right? That oh my god ma'am, my hands ma'am not working ma'am. How do I write yes ma'am? Ma'am, it takes like millions and years to write yes ma'am ma'am. How do I write it ma'am? So difficult ma'am. What a task you have given us ma'am. You prepared ma'am PPT, it's okay ma'am. You have taken the best content, it's okay ma'am. You have taken the questions, it's okay ma'am. Ma'am, how do I write yes ma'am there? Right? Chalo, I think I need to give you break as well. So I'll give you break for 2 minutes and I'll see if you guys answer something in the chat box. I'll see that. See that. Very lazy people you are, I have seen. Okay, so guys, let's see. Next is enthalpy of atomization. That is, if it is an enthalpy change on breaking bonds in 1 mole of substance. That means in 1 mole of substance, breaking bonds in 1 mole of substance completely to obtain atoms in the gaseous phase. The atoms will be in the gaseous phase. It is denoted by delta HA, right? That means if you have H2 and this is 1 mole of the substance, when you break this bond, that is called and convert it into gaseous atom, this enthalpy that is required or released is called as enthalpy of atomization. For a diatomic molecule, enthalpy of atomization is equals to bond energy, right? Okay, bond energy is the enthalpy to break the bond, right? For example, if I have, now I'll just tell you one example, one more example here, right? It would be better to write it that way. Wait a minute. So now if you see this here, right? Now if you see this here, that is going to be, wait, if I write CH4, right? If I write CH4, now in this case, right, the enthalpy of this particular reaction to break these 4 bonds, that is called as bond dissociation enthalpy of these things, right? Okay, so if I talk about, this is equals to 4 into the enthalpy to break these 4 bonds and convert it into 1C and 4H atoms. What you will require is, you need to break 4CH are required. You need to break 4CH. 4 enthalpy of atomizations are required, right? So total bond energy of this particular thing is, total bond energy here, total bond energy to break CH4 is equals to bond energy required to break CH 4 times of that, right? That this is what we are explaining. But when you talk about this H2, to break this particular bond, the energy that you require is also delta H of atomization, and that is also bond energy. And so you can write, this is also the bond energy, right? Okay, so you can just directly write it there. This is CH, this is CH, this is CH, and this is also CH. Okay, right, everyone? Now let's see, next thing we have lattice enthalpy. Okay, what is lattice enthalpy? Bond dissociation enthalpy is to dissociate, to break this bond, how much energy is required. Atomization is when you convert it into atom. Enthalpy of atomization is when you break it and you convert it into an atom of gaseous. When you convert any, when you break any bond and you convert that into a gaseous atom, that is called as enthalpy of atomization. Bond enthalpy is when you break the bonds, the energy required to break this bond, to require this bond, this bond, this bond, right? That is called as bond dissociation enthalpy. To dissociate a bond, how much energy is required. And total bond enthalpy of this CH4 molecule will be equals to 4 into bond energy. This will not be bond, this will not be equal to atoms, bond enthalpy of atomization. Atomization is when you convert it into gas, right? That is enthalpy of atomization. When you have gaseous atom, right? Now lattice enthalpy. Lattice enthalpy is when you talk about an ionic compound, right? Enthalpy change which occurs when 1 mole of ionic compound, you have 1 mole of ionic compound that is dissociated, right? Dissociates into ions in gaseous state, right? You have 1 mole of NaCl, that is a ionic compound that dissociates into ions, right? Of in the gaseous state. This is also in the gaseous state, this is also in the gaseous state, that is called as lattice enthalpy, right? Okay, if you see this in chemical kinetics, you must have done Born-Haber cycle, right? So I'll just explain you that here. If you see this thing here, if you see this thing here, This thing will be firstly ionized. So you will have ionization enthalpy, Na solid, but this is Cl negative, right? This is in the gaseous state. But here this will be firstly converted to Na positive in the gaseous state. Then it will be, right, then it is converted to Na positive gaseous state, and this is converted to already in Cl negative gaseous state, right? So this is the enthalpy that is required here to convert this solid into the gaseous state ions, that is called as lattice enthalpy. Okay, this will be called as lattice enthalpy. Next is enthalpy of hydration, and that is only for ions, right? If you have any ion which is in the gaseous state, when you put it into water, this converted into aqueous state, then the enthalpy that is there, that is called as enthalpy of hydration. You don't have to remember these values, these are just examples that I'm giving you. That for example, you have any positive ions, water molecules will be attached, will be attracted by the positive ion, right? Right, like this way. Now this is what we call hydration, that this particular ion is being hydrated. So energy change when 1 mole, and always remember I am always talking about 1 mole here. 1 mole of ion undergoes hydration. It is denoted at delta H of hydration. If solvent is other than water, then it can also be called as enthalpy of solvation. If solvent is something in, then this same enthalpy is called as enthalpy of solvation. Next is enthalpy of solution. See how many enthalpies you have here. So many. Enthalpy of hydration is ions that is being hydrated, and enthalpy of solution is of a substance. I am not saying it should be an ion, I am saying any substance, is the enthalpy change when 1 mole of it dissolved in specified amount of solvent. When one amount of any substance is dissolved in a specified amount of solvent, the enthalpy that is required or released, that is called an energy of solution. For example, you have NaCl solid that is converted to NaCl aqueous, that is enthalpy of solution. NaCl solid, right, then it is further converted to aqueous ions, that is also called as energy of solution. But if Na positive in the gaseous state, that is converted to Na positive in the aqueous state, that is called as enthalpy of hydration. Okay, understood? What is enthalpy of hydration? What is enthalpy of solvation? When some ion, it is converted to, it is hydrated by some other solvent, that is solvation. Solution is when you have any substance that is put in water, right, that is called as that is called as solution, because you are making a solution here. So you have a solute and you have a solvent, you are making a solution, the enthalpy that is there, that is called as enthalpy of solution, right? Okay. Then see this thing. If you see AB is a solid, right, firstly you will use enthalpy of solution to convert it into aqueous ions, right? Then either you can directly do this, or you can say firstly you will break it, you will divide it into gaseous ions. So the enthalpy that you use, you have a solid which is ionic in nature, you convert it into gaseous ion, that is lattice energy. So this is lattice energy. Then you convert these gaseous ions in aqueous form. This is enthalpy of hydration. Okay, so either you can go this way, either you can choose this path, or you can choose this path, you can choose this path, and then this path here, right? Okay, so that is, this is path 1 and this is path 2, whatever you can choose here, right? Okay, enthalpy of solution. For most of the ionic compounds, delta H solution is positive. We say most of the ionic compound delta H solution is positive, and the dissociation process is endothermic. That means what we are saying, most of the ionic compounds, right, energy is required to dissolve it in water. It is not released, it is required. It's an endothermic process. If lattice enthalpy is very high, the dissolution of the compound may not take place at all. That means if you require a very high amount of energy here, let's say to break that particular solid into gaseous ion, you require a lot of energy, then in that case, it is very, very difficult for you to proceed through this path. For example, you want to purchase a bag that is worth let's say 50,000. Now you will be like, why do I purchase a bag of 50,000, right? If I can easily have a bag of 1,000 or 500 or something rupees. Similarly, if lattice energy, to do that work you require a lot of amount of energy, that thing will not happen. Only the dissolution of the compound may not take place. For example, fluorides are less soluble than chlorides because a lot of energy is required in case of fluorides. Now let's see a question here. JEE 2020 question. Let's see that. Okay. Let's see this question that says lattice enthalpy and enthalpy of solution of NaCl. Is this? Okay. Lattice enthalpy is this, solution is this, hydration you have to calculate. See, solution is, they're talking about NaCl. Solution is to convert NaCl directly to Na positive aqueous and Cl negative aqueous, right? And here when you convert it into Na positive gaseous and Cl negative gaseous, that is lattice enthalpy. That is given to you, lattice enthalpy is given to you 788 kilojoules. Okay, 788 kilojoules. Wait a minute. 788 kilojoules. And from this to this, if you go, let energy of solution, right, required here is, wait a minute, solution is this, not this is hydration that you have to calculate. Here solution is given to you, that is 4 kilojoule. And now they are asking you what is this. Now what I'll say, you go to this part, this is 4 is equals to lattice enthalpy plus hydration, right? So lattice enthalpy is 788, this is 4, this is plus hydration. So hydration will be equal to 4 minus 788, that is minus 784, right? So C is going to be the correct answer here. See, such a simple question they have asked you here, right? Right? Okay, okay, Louis. Got it? So now let's see enthalpy of transition, right? Enthalpy of transition. It is an enthalpy change when one mole of allotropic form changes to another. One allotropic form is changing to another allotropic, carbon to carbon, graphite to diamond, the enthalpy that is there. When allotropes forms are interchanged, that is enthalpy of this transition, right? Then enthalpy of formation of ions, right? You have Cl2, it is enthalpy change when one mole of hydrated ion is obtained. Hydrated means aqueous ion. 1 mole of aqueous ion is obtained from its element in its standard state. Element in the standard state. So Cl2 is in the standard state, like Cl2, O2, H2, all these are the standard states. Okay. So when it is in the standard state, and when you break it into Cl negative aqueous, when you have the ionic form, hydrated ionic form, in the aqueous form you have it, that is called as enthalpy of formation of ions. Here we are forming the ions. And whenever we talk about enthalpy of formation, that is there from the elemental and the standard states, right? And only 1 mole is prepared here. 1 mole of hydrated iron is obtained here. I am not saying this should be 1 mole. No, I am saying this should be 1 mole. This should be 1 mole. Okay? Now, next is enthalpy of formation. So, there is a difference in enthalpy of formation of ions and enthalpy of formation. Enthalpy of formation of ion says that you have reactant in the elemental state. We are not defining that the reactant should be 1. We are saying reactant can be how many number of moles. But the product is ions in the hydrated state, that means this state, in the hydrated state, right? And that only 1 mole of ion you required, okay? But enthalpy of formation is different. It is enthalpy change. When you form, now here form 1 mole of a compound from its elemental state. Standard enthalpy change for the formation of 1 mole of compound from its elemental state in their most stable state of aggregation, that means their standard states here. So if you talk about this particular reaction, is this, see, ma'am, is enthalpy of reaction different? This is enthalpy of reaction, this is enthalpy of reaction, this is enthalpy of reaction. You discuss, this is enthalpy of reaction, this is enthalpy of reaction, this is enthalpy. All of these are enthalpies of reaction only. But you have to define it, right? So all reaction means in that reaction how much enthalpy is released, but now we are specifying which is specially divided into these parts, right? Like we are humans, but we are divided into male, females and other genders, right? So if you see here, this particular thing is 1 mole. 1 mole of product is formed from the elemental state. So carbon is in the elemental state, that is graphite. Hydrogen is in the elemental state. Oxygen is in the elemental state. And here 1 mole of this is formed. That's how we can say this is actually enthalpy of formation. And questions on enthalpy of formations are asked. Okay. Then note down whenever we have to define, this is a very, very important thing that they ask you, right? That whenever you have to, let's say they have given you enthalpy of formation of this, enthalpy of formation of this, enthalpy of formation of this is, all of this is given. And always remember, enthalpy of formation of standard states is 0. That means no enthalpy is required to make carbon graphite. It is natural. H2 is natural. O2 is natural. So that's how they will not have any enthalpy of formation. But this whole thing is enthalpy of formation. So whenever you have to define the enthalpy of reaction and enthalpy of formation, right? So the standard enthalpy of formation is the most stable of any element is 0. Because there is no formation reaction needed when the element is already in its stable state, right? That's what I told you. Delta H formation of carbon, hydrogen, graphite, that is 0 only. And enthalpy of that reaction is nothing but always in terms of formation, you will always write it as product minus reactant. I'll show you how. Okay, I'll just show you with the help of questions how do you do that. Which of the following, this is a very old question, right? This is, I just want to tell you how to answer these things, okay? These much simple questions are not asked, but still I just want to show you that. Which of the following reaction defines delta H formation? Here it is from the elemental state. No, graphite is the elemental state. This is from the elemental state. This is from the elemental state. But here 2 moles are formed, so it is also not correct. Here 1 mole is formed and this is not the elemental state. So only B is where you have 1 mole of product is formed and these are the elemental states. So answer will be B is the correct answer here, right? Okay. Then there is enthalpy of state change. Okay. I think after that a lot of questions are going to start. Yes. After that we are going to have some really interesting questions. Okay, see this. Enthalpy of state change. Enthalpy of fusion. What is fusion? When you convert, you do melting, when there is melting, solid to liquid. Vaporization is liquid to gas, and sublimation is solid to gas, right? So heat change during conversion of, and all of this is 1 mole. 1 mole of solid, this is 1 mole of liquid, this is 1 mole of solid. That means all the reactant has to be 1 mole here, right? So this is about the phase change, phase transformation, when the state is changed. Enthalpy of dissolution, we have done enthalpy of solution hydration, but what is this dissolution? The amount of heat released or absorbed when 1 mole of a substance is dissolved in water, right? You're just dissolving 1 mole of substance in the water, that is called as enthalpy of dissolution, right? Okay. Ma'am, then what was hydration? Hydration was when you have a when you have a ion, right, that is converted into gaseous, that is converted to aqueous ions, that is hydration. What then, ma'am, what was solution? Ma'am, what was dissolution, difference between solution and dissolution, right? So in solution you have a solvent, you add solute into it, right? And that is the enthalpy of, and solution and dissolution don't have that much difference here, right? They're almost on the same category only, right? Okay. So enthalpy of heat release absorbed when 1 mole of a substance is dissolved in water. Here we are specifying, right? Then enthalpy of dilution, amount of heat released when solution is diluted by adding water to it. Dilution means when you add more water, already it is water. Here it is already enthalpy of dissolution and enthalpy of solution. Solution, yes. Enthalpy of solution and enthalpy of dissolution is same only, almost same only. Right? Here we are specifying it is water. There we say in a solvent. When we say in a solvent, that is solution. When we say it is water, it is dissolution. Dilution is when you add more water. It's already a water and it's already a aqueous solution. You add more water. That is dilution. Okay. Now this is quite important. That is enthalpy of combustion. Combustion is, it is enthalpy change when 1 mole of a substance, you have 1 mole of a substance that undergoes complete combustion. Now in this case we say, if you see here in the formation, what we said in the formation, bacha, I said the product has to be, product is 1 mole. In the combustion, when I talk about combustion, we are saying reactant has to be 1 mole. Here reactant has to be 1 mole. Okay. So this is 1 mole and you have O2 and you have combustion there, CO2 and water is formed, and this enthalpy of this reaction that is released, that is called as combustion. Okay, that is known as combustion, right? Okay. So enthalpy of combustion, calorific value of foods and fuels, amount of heat produced in calories on joules when 1 gram of a substance, if you have 1 gram of a substance, right, food or fuel is completely burned or oxidized, is known as calorific value. When 1 mole of a substance, we say amount of heat produced when 1 mole of a substance, that is in calorie or joule, when 1 gram of a substance, here I am saying this is in gram. Here I am saying this is 1 mole. Okay, here I am saying this is 1 gram. 1 gram of a substance, that is called as the calorific value that you have. Okay, right? So the calorific value here will always be, because guys tell me, this is for 1 mole. This is for 1 mole. 1 mole means, if I write it here, molar mass here is, this is 1 mole, weight, molar mass of CH4 is 16, so weight will be equals to 16 grams. So this value is for 16 gram. If I want to draw the calorific value, I'll just divide this delta H by mass of that compound. That will give you your calorific value. So always you can say this here, calorific value is equals to, right, I'll just write this here, calorific value is equals to calorific value calorific value is equals to the heat delta H of combustion divided by weight of substance. Okay, weight of substance that was under combustion. Okay, that is going to be the value. How do you uh, solve calorific value? And do you see one thing here? Whenever you write the delta H of reaction in terms of formation, it is product minus reactant. In case of combustion, it is different. In case of combustion, this is very important point. In case of combustion, it is reactant minus products. In case of combustion, it is reactant minus products. You see this here, reactant minus products. Okay. So in this case, it is going to be reactant minus products. Tell me. But no, they are not same fuel as they are just the units, okay? They are just by convention that food is taken in calories, okay? Yes, that is just by convention, right? It's not like we can't tell the food calorific value in kilojoules. You can definitely tell, okay? It's not like that. So let's see the question here. JEE Mains 2022 question, that is at 25 degrees Celsius, 1 atmospheric pressure, the combustion of benzene, acetylene are given to you respectively. The change in enthalpy of reaction of this combustion of both of them is given. Delta H of reaction is equals to delta H of reactant minus delta H combustion, and this is combustion of product. Whenever they have given combustion, I'll always use reactant minus product. Here reactant is this, so it is 3 into C to H2 combustion value delta H combustion for C2H2 minus this is delta H combustion for product is C6H6. Okay. So combustion for C2H2, combustion of benzene and acetylene. Benzene is this. So it is minus, benzene is minus 3268. Okay. It is minus 3268. Okay. This is 3 into this is 3 into what is C2H2? That is acetylene is given to be minus 1300. Solve this and you will get your answer. Okay, solve this and this will be the delta H of reaction. So delta delta H of reaction is what? That is reactant minus product. Latest question, JEE 2022. So the calculation, the application part is not difficult here. Will there be continue videos uploaded? Definitely there will be 11 content as well that will go on, right? Okay. So yes, this I directly told you, so I'll just delete this slide, right? Next is delta H hydration. What is hydration? That I have told you already. Enthalpy change when 1 mole of anhydrous or partly hydrated compound combines with required number of moles of water, that is water of crystallization, to form specific hydrate at a specified temperature and pressure. Now when anhydrous CuSO4 forms water of crystallization, with water of crystallization it forms hydrated copper sulfate, that is called as delta H of hydration. Okay, then very important bond enthalpy that you were asking me before as well. Let's talk about this in detail and then we'll do questions on that, right? Let's see bond enthalpy here. If you see this here, tell me, if you see this here, I'm so sorry. So bond enthalpy is the amount of heat required to break 1 mole of bonds. To break 1 mole of bonds. When you want to break 1 mole of bonds, the amount of heat required to break 1 mole of bond, the amount of heat released during the formation of 1 mole of bonds, right? So what exactly is there? When you have 1 mole of compound, the amount of heat that is required to break this, the amount of heat that is required to break this. 1 mole of compound, that is called as bond enthalpy of that compound, right? Okay. So enthalpy of reaction, how it is related? See, in formation you used to do, how enthalpy of reaction is related to formation? It is product by reactants. In combustion it is reactant by product, reactant minus products. In case of bond energy as well, this is reactant minus product. So this is also quite important, that this is also reactant minus product. Okay. So for example, this thing is given, what is delta H of reaction? That is bond enthalpy of C2H4. What is C2H4? C2H4 is this. That means here the bond enthalpy of C double bond C, 4 times CH. Bond enthalpy of C double, reactants is this, na, C double bond C, 4 times CH. Then bond enthalpy of HCl, right, this bond. Add all of them, minus C2H5, C2H5, Cl. So that means you require 1, 2, 3, 4, 5. 5 CH bonds you will break, 1 Cl bond you will break. So you will say minus bond enthalpy of 1 Cc and 5 CH bond, right? And 1 Cc bond as well and 1 Cl bond as well, right? So that is how you define it in the terms of bond enthalpy or bond energy, right? Okay. I'll just show you a question based on that, how it is written. If you see JEE 2006 question, that is, if this much of bond energy, CH, C double bond C, these energies are given to you, the value of enthalpy change for this reaction, what is that? So if you see this reaction, it is going to be reactant minus product. So that means bond enthalpy of C double bond C you will add plus 4 times CH plus HH bond enthalpy minus of product is 1 CC bond you will have and 6 CH bond. So 6 into CH bond, okay, minus 1 CC bond. Okay, that will be there. That is your delta H of reaction. If you see this here, CC bond is what? CC bond, this is for CH, this is for CC, this is for C double bond C, and this is for HH, right? So C double bond C bond is 615 plus 4 of CH is 414. So this is 4 times 414 plus of HH. HH is 435, right? Minus 6 times CH. That is, you can, add it there. It will become 2 of CH only. So I'll just write it here. That is 414. This and this will directly be cancelled. Minus 1 of CC. CC is given to be 347. Okay, solve this and you will get your answer, right? Okay, yes. Okay, solve this and you will get your answer there. right? That's how you solve bond energy of reactants minus product, and that's how you solve this, and you will get your answer as C is the correct answer here, right? Okay, now let's talk about resonance energy. Now, what you see? Energy of most stable canonical form. Canonical form is the resonance structures, and out of them, one structure is most stable. The energy of most stable canonical form, and this is the energy of resonance hybrid. The difference in the energy of resonance hybrid and the most stable resonating structure is called as resonance energy. Okay. Now, if you talk about resonance energy here, let us see. When a compound shows resonance, there is considered difference between heat of formation as there is a considerable difference between the heat of formation as calculated from bond energy and that determined experimentally. So, if you talk about resonance energy in terms of heat of formation, experimental actual heat of formation minus calculated heat of formation, that is different, right? Here also calculated heat of formation is combustion is also different, and actual experimental is different. Why? Because of this resonance hybrid and resonance structure. So you don't get the actual energy what you think, what you calculate in the books, that is different. What you think, it should be like that, and in experiment what you find out while doing the experiment, that is different. That is why, because of difference in resonance hybrid and resonance structure, because of the energy difference between resonance hybrid and resonance structure, when you actually solve a molecule which is showing resonance, it will show different heat of formation and combustion for actual and experimental, right? Okay. And in case of heat of formation, it's experimental minus calculated. What is in the theory? This is expectation. This is expectation. Expectation versus reality is different. This is reality minus expectation, and this is expectation. That is what you calculate in the theory. Expectation, and this is reality. Since resonance stabilize a molecule, resonance energy is always with the negative sign. Okay, so always resonance energy will be in the negative sign. Let's see this question. 2013 question that is based on this thing. Calculate the resonance energy of N2O from the following data. Delta H formation is given. Bond energy of these bonds are also given. So see, this is what you will calculate, what you will think, and this is what is reality. So let's understand how to firstly answer what is calculated. How to firstly answer which is calculated. For the N2 molecules, from the formation, I'll talk about N2 plus half O2 in the elemental state. This will give you N, right? Now, what you have, N triple bond, this is NO bond, this has NN bond as well, O double bond O as well, that is written. So what you will see, that delta H of this reaction is nothing but delta H formation, because delta H reaction is for every reaction, but when I say 1 mole of the product is formed by elemental state compounds, right, then it is called as formation. Whenever you write formation here, whenever you want to calculate the delta H of reaction in terms of bond energies, that will be reactant minus product. So it will be enthalpy of N triple bond. I'll just write bond enthalpy of N triple bond N plus half into bond enthalpy of double bond O minus 1 into bond enthalpy of N double bond O, right, and N double bond O and minus N double bond N, because it is N double bond O. this kind of situation is, this kind of molecule it is, na? This kind of molecule this is, na? N2 is nothing but it is N. Okay, so we have added N double bond O and N double bond N. That's how you calculate this. So delta H formation, which what we are doing is we are doing the calculated part. Calculated will be N triple bond is 946. This is plus half of bond in the O double bond O. O double bond is 498. Half of 498. Right? NO is what? NO is written on the last, that is 607. Okay? And minus of N double bond N, that is 418. Solve this, and what will be the bond energy? What will be the resonance energy? Resonance energy is going to be bond energy of the expectation. This is reality versus expectation. Reality minus expectations here. So reality is this is the reality, that is 82, minus what you have calculated here, delta H formation of calculated. What you have calculated here, you will put it here and you will get your answer. Okay? Yes. If you join a lecture in the end, then how you'll be able to understand? Okay, we have solved it already. This is going to be 170. Then you put the value here, observed minus calculated. Then you put it, I will say reality minus expectation. Okay, reality is this, calculated is that. You solve it and you will get your answer. Okay. Next question is, the experimental and calculated heat of formation for is given. What is the resonance energy? So it is quite simple, right? Resonance energy they are saying, and here heat of formation is given. Resonance energy, which are will be what? Reality minus expectation. Reality minus, you see that meme, na? You are so familiar with that meme, reality minus expectation. Reality will be the one that is given in the question. The experimental, that is given to be 20. Experimental means which is real, what you have experimented. Calculated is what you expect after calculation, that is 360, right? And that is going to be your answer here, right? Okay, solve this and you will get your answer. Minus 5152 is the correct answer here. Okay, that's how you answer. That's how bond energy is related, that's how resonance energy is related to formation combustion. Okay, right, everybody? Understood? Tell me. Whew. Let's see more. We are almost towards the end of the lecture. Okay, we are towards Hess's law. We'll see then how to solve the Hess's law questions, and that is the last topic that we are going to discuss. Okay, let's see. Next lecture will be chemical equilibrium, that I'm going to start, right? I think on Monday I have the session. Wait a minute, let me see. It is it is on Tuesday. Okay, so here you have Hess's law of constant heat of summation. So what Hess's law states? Hess's law says that if the reactant is getting converted to product, you go to this path, that is the delta H of reaction. Now this can also be given by this, then this, then this. So this delta H of reaction is equals to the addition of all these heats, delta H1, delta H2, delta H3. That is Hess's law, right? So chemical reaction can be made to take place in a number of ways, in one or in several steps. The total enthalpy change is always same. It means it is independent of intermediate steps involved in the change, right? It is not dependent upon these things. So if you, even if you do simply, it means it is independent of the path. You follow this path or you follow this path, that is the same thing. So we are going to equate it, right? It is independent of the intermediate, it is independent of the path. Let's see the question here, that is the enthalpy of combustion of carbon and carbon monoxide are this and this. The enthalpy of formation of carbon monoxide per mole. Now, combustion is given to you. See, carbon monoxide you have 1 mole and it will be formed by carbon and O2. Enthalpy of combustion of carbon and carbon monoxide are given to you. Enthalpy of formation of 1 mole you have to tell me. Okay. For the enthalpy of formation, you will solve it. Enthalpy of combustion of carbon and carbon monoxide are given to you. Combustion is already given to you, that how carbon monoxide is combusted, right? The enthalpy of combustion, if you say carbon plus O2 give rise to CO2, that is the enthalpy of combustion of carbon. Monoxide is CO plus half O2, that is CO2. These all things are given to you. Now you have to solve this thing, that is this thing. Now how do you solve it here? Now if I add these two equations, CO2 will be cancelled, right? This will become C plus, no, if I subtract these two, if let's say this is the first, this is the second. Now if I subtract 1 from 2, then this is minus, this is minus, this is minus, this will be cancelled. This will become carbon minus CO, and this is minus of, this is 1 minus half is half of O2, that this will come to this side and this will become CO, right? That means this equation I'll get from there. So what I can do, I can just subtract 1 and 2. So delta H of this reaction, you can write here from Hess's law, right? Delta H of, because I am saying either you follow this path or you follow these two paths, that is the same thing. So delta H of this reaction, which is also formation of CO, is equal to 1 minus 2. Let's say this is 1, this is 2. So this will be minus 393.5. If this is subtracted, this will be minus 283.0. You solve this and you get your answer. Okay? Yes? So, next is, let's see, next question here, that is oxidizing power of chlorine in aqueous solution can be determined by parameters indicated below. So this is one thing. First you will dissociate it to gaseous molecules, right? Then you will add one electron here, then it will become Cl negative, that is enthalpy that you are giving, right? That is electron gain enthalpy, right? Then you are converting this into aqueous, that is hydration. So energy involved in the conversion of this to this is what? You add all these enthalpies using the data. Dissociation is given, Cl is given, right? Electron gain enthalpy of Cl, and hydration is given. See, this is a very old question, but here they have given you this thing. But if they ask you in 2026, they will not give you this thing. They will just ask you that these are the values that is given to you. Answer that what is the enthalpy of, they can ask you directly, enthalpy of, what is this? Enthalpy of ionization. Yeah, ionization, it was enthalpy of hydration. Okay? Enthalpy of hydration. So you're adding this thing here, right? Okay, so you can just directly calculate this here from Cl negative to this is Cl this. Now here we are taking out from gaseous to Cl negative. So what you have to do, you just have to all these values, right? This is half into this, add all these values and you will get your answer there, right? Okay. So all you have to know is that which is enthalpy, what kind of enthalpy is there, how do I convert the Cl2. Overall, you go from this to this, or you do it in steps. That is the same thing, right? So that is your question of Hess's law. That's how they ask you the questions. Okay. Next is they are saying under the condition, under the reaction, this is a question, this is the first reaction. If N2O5 solid is formed instead of N2O5 gaseous, if you have solid in the above reaction, delta H value will be what, right? Delta H sublimation of N2O5 is this. Now, if instead of gaseous you have solid, then again to solid to gaseous you will use some value. Now, solid to gaseous value you use is this one. That means this much value will not be released here, right? So 54 is the value that won't be released here. So you convert N2O2 to gaseous, then this is the reaction. If you convert it into solid, then some amount of heat is required that we don't know. But solid to gases, solid to gas, the sublimation is 54. So you can say by Hess's law, if I say this is 1, this is 2, this is 3, then you can say 1 is equals to 2 plus 3. 1 is nothing but 111 minus 2 is nothing but that delta H that we want, and 3 is nothing but 54. So delta H is equals to minus 111 minus 54, and that is going to be the correct answer here, right? Okay, right, everybody? Understood? See, now we are just towards the end only. Then guys, we have Kirchoff's equation, right? We have Kirchoff's equation. Let's see. Now from here, so say they don't ask you the questions, but you must do this. It is in your syllabus, so I'm just writing it here. Variation of heat of reaction with temperature. If you have at temperature now, Lewis was asking one question again and again. Ma'am, what if the temperature changes? Delta H will also change? Yes, this is where Kirchhoff laws is based on this part only, that when you change the temperature, delta H changes. So let's say delta H at temperature T1 is this, T2 is this. So it is delta H of T2 minus T1 temperature. T2 minus T1, the temperature also will subtract, that is equals to delta of Cp. Where what is delta Cp and Cv? Sum of heat capacity of products minus sum of heat capacity of reactants at constant pressure here, because this is a term of where constant pressure we use. This is constant pressure, because it is constant pressure, that's why we are using delta H, and this is constant volume. And this is constant volume. Okay, so for constant volume you use delta U at temperature T2 minus delta U at temperature T1 by T2 minus T1 is delta Cv. Okay, yes, yes, definitely will do that, don't worry, right? Okay, different sessions especially dedicated to PYQs will be there, right? Okay, yes. So guys, that's it. If you see JEE 2023 question, that is, which of the following reactions are correct? So delta U is equals to Q plus P delta, we know. Delta U is equals to Q plus W, and W is nothing but it is minus P delta V. So this is absolutely wrong. Delta G is equals to delta H minus T delta S, that is correct. Delta S is equals to Q reversible by T, that is absolutely correct. Delta H is equals to delta U minus delta N RT, no, it is delta H is equals to delta U plus delta NG RT. It's plus here, so this is also not correct. So only B and C are correct here. So answer will be B is the correct answer here. Okay. IPL match, go and watch that, right? Okay, so that's it for today, guys. Now we have completed thermodynamics and thermochemistry. It was a very important chapter, and next we are going to do chemical equilibrium on Tuesday and Thursday. On Tuesday, I'll have your class at 6 p.m. and on Tuesday and Thursday, I'm saying Tuesday and Wednesday. Tuesday, I'll have your class at 6 p.m. and on Wednesday, I'll have your class at 9 p.m. Okay, or 8 p.m. actually. 8 p.m. I'll have your class. Okay, so that's it for today, and I'll see you all tomorrow, not tomorrow, on Tuesday in chemical equilibrium. See you all. Bye bye. And do write it down in the comment section. How do you like these sessions? Do you want more of the sessions, detailed session, or you want one shots? I want to know that are you 2027 aspirants? Are you 2026 aspirant? Right? So that we can, you know, take up content for both of the students, and just tell me what are you preparing for 2026 or 2027, and what you're right now expecting. Is it question practice? Is it one shots? Is it detailed videos? Is it detailed lectures? Whatever you expect, right? Okay. Yes. Okay then. Bye bye. Take care. Bye.